did is basically looking at global and local features in the image. So something that we learned from last year is actually that scene information is very important for this particular task. So here are models for trained on ImageNet, and these are models trained on visual sentiment ontology. And you clearly see that all of these models perform better if you just use the features and a classifier like a support vector machine. So we also leveraged global information from scene pre-trained models. And in particular for this task, what we figured out that they are very good for discriminating between flood and non-floods. However, if you look at the passability classification, it's not very useful. So this visual sentiment ontology, it consists of adjective noun pairs. So usually it's used in sentiment analysis. However, they also have a lot of important adjectives that are also relevant for this task. So for example, we used a model which is called ResNet or XResNet, cross-residual connections. And there are 3 outputs. The one is predicting adjectives, nouns, and adjective noun pairs, so the combinations of them. And if we apply this to these 2 models, for example, you would see that the probability distribution over the whole last feature vector is very similar. And you could also get very similar results such as muddy river, wet road, rainy street. So it's not very helpful for the second task of road passability. And that's where we actually also tried to use local information. So we had 2 hypotheses for our approach. One was that local features are very important for especially the passability problem. And that's also if you look at these approaches such as car, person, similar to thing use approach. And the second is that fusing this together with a global context helps the final classification, since you cannot always rely on local information because you put a certain constraint into your classifier. So what we did here is also a 2-step approach. First, we used a right ResNet. It was trained on places for the scenic information. And we used this feature extractor, trained a support vector machine with a radial basis function kernel. And we already got on our validation sets quite good results for just discriminating between evidence and no evidence. And for the possibility, we did a couple of experiments in investigating into local features, into global features, and their fusion. So for the global features, you see here a couple of networks that we used. One common theme is here also similar to the result on the first slide, that the scenic information here is quite better compared to the ImageNet models. So it is very important. And for the local information, we have the following pipeline. So we use FastRCNN. It's an object detector, which was trained on Pascal VOC. So we extracted for our dataset 6 different classes: cars, persons, bicycles, buses, boats, and motorbikes. For motorbikes and bicycles, we just had a few examples, so we didn't investigate into this. For persons, we basically cropped, or basically for the other 4 categories, we cropped these patches out of it and trained a second network, which was very small. It was a LeNet, just to classify whether this small patch shows evidence of passability or not. What we figured out is for person, actually it didn't work out that well. So we didn't get any results, any significant results, because there are quite many different variations in how persons are in the image. Like in this case, it's very similar. It's very simple because you see the whole person, but sometimes you see person which are in the car and you just see the upper part. So this didn't work for us at all. And what we did at the end is basically combining cars, bus, and boats into one class and then training one network to classify this. And we also saw that it's quite commonly in the dataset. So in about 50% of all the images, we saw at least 1 or 2 of these local concepts in the images. Yeah, exactly. And then we basically tried to classify it with this small network here. And we got at the end validation results on the images where we have this local information of 72% 2% accuracy. And if you compare this with the global information that we got previously, so the lower bound was 73 from the ImageNet pre-trained model, and this one was the upper bound from the scenic model of the global features. So we are quite similar compared to global features. And the idea was then, so the first hypothesis that local features are important for this is certainly true. And then we investigated into the second approach on fusing the local but also global features. And for this approach, we tried a couple of different approaches like late fusion and also in fusion, where we used the last fully connected layer of the small LeNet for the global features. However, we got some results. So here you see basically the results of the model with the global context, and here with the global and local, so the fused context. For this particular network, it got a bit better. It's not significantly, and for this one, it actually got a bit worse. So at the end, basically, local information are quite helpful for us. However, we didn't get a very big benefit from it. So something that we would like to investigate further is to add more information into the local features. Right now, it was quite restricted that we used a very small network to classify this, and we also always resized the images to the same input. So one approach would be also to use fully connected networks to basically allow arbitrary input size. And the other idea would be also to use also segmentation networks, such as the ones which are trained on cityscapes, for example, where you also have information about the lanes, about the traffic signs and so on, and incorporate more local information into this approach. And then fuse it, since we have then a better local classifier. Yeah, thank you very much.